All right, here we go on the warm up. So it says solve these equations. And what I really want you to look at while you're solving these equations are the inverse operations that we're using. So if you're doing this at home, you should pause the video and solve these real quick. Great. All right, so on the first problem, what do we need to do? Well, we're adding 3 to x, so we need to subtract 3. And when we subtract 3 from both sides, then the result is x equals 2. On the next one, we are subtracting 8 from x. To undo the operation of subtraction, we add 8 to both sides. And when we do that, we get x is equal to 6. 3x equals 12. We're multiplying, so we divide by 3, and we get x is equal to 4. Hopefully this feels good so far, not like much trouble. Even this next one, hopefully there's no trouble here. We just square root both sides to undo the square. So we get x equals, maybe a little tricky here. What's going to be tricky here? Anybody? Morning, Shep. X equals what? Positive and -4. So that -4, it might be a little bit of a tricky part because -4 times -4 is positive 16. All right. Now we have a square root of x is equal to 4. We square both sides to undo the operation of square root. And here we get 16. And this next one's interesting. Why is this one interesting? Anybody know the answer? Oh boy, not many people feeling brave this morning. Well, I know that so I'm thinking, how many times do I need to multiply 3 by itself to equal 9? Well, the answer is 2. So if I put a 2 in here for x, 3 squared is 9. All right. So an inverse operation undoes the original operation. Go back to the warm-up and name each of the inverse operations. Which inverse operation do you not know yet? Well, here we said subtract, add, divide, square root, square. Inverse of that. What's the inverse that allows me to get to there? Does anybody know? Is this mic on? Do you guys hear me? All right. Thank you, Tommy. I was worried that I was just like my technology was all messed up. Does anyone not have any ideas what this is? What the plan is? No? All right. Logarithms. Woo! Logarithms. I know you guys are excited about new units. Well, here we are in a new unit. The unit is log. Logarithms are defined as the inverse of raising a given number to various exponents. So really, this idea, this raising a given number to various exponents, really what we're saying there is exponentiation. So we're going to convert each of these equations to a logarithm, and then we're going to use a calculator to solve for x. All right, so when we convert these logarithms, and this would be a great time for you to be taking notes, I want you to make sure that as you're converting them, you read it the way that you write it. And here's what I mean. So for the first one here, 3 to the x is equal to 243. What we have is we have log base 3 of 243 is equal to x. And the reason why I say to read that the way that you write it, notice that I said base 3. So the base of the logarithm is the base of the exponential. So bases are here, the exponents are here. So notice that really, since x equals a logarithm and x is an exponent, that means that a logarithm is an exponent. A logarithm is an exponent. So when we write something like this, we need to remember whatever that number is, we're talking about an exponent there. Okay? So I'm going to bring up a calculator. I'm going to bring up the Desmos graphing calculator. And it needs to be the graphing calculator here because the regular calculator doesn't have the nice exponential, the logarithmic option. So the Desmos graphing calculator has this keyboard down here. And when I click on it, it doesn't give me logarithms anywhere. So I need to click on functions, and I still don't see logarithms anywhere. I need to go to miscellaneous. And then here's logarithm base A. Notice this one doesn't have a base. It's just log. We want log base A. And that allows us to then write in log base 3 of 240, log base 3 of 243. And so our answer then is right here, 5. So I can make that small. And I'm going to get this kind of up and out of the way, but so that we can see the screen and the calculator at the same time. Sorry, this is taking me a minute to do this. There we go. All right, so we have log base 3 of 243 is equal to x. So that tells me that x is equal to 5 here. And I can verify this. If I wanted to verify it, I could go 3 to the 5th power, and I see there it's 243. So x is 5, so 3 to the 5th power is 243. All right, so the next one is 10 to the x is equal to 0.01. So writing this in the form of a logarithm, so we convert it to the form of a logarithm in order to answer to solve for x. So we have, log base 10 of 0.01 is equal to x. And sometimes the thing that we're taking the log of, we call that the argument and some of the logarithm. And sometimes we put it in parentheses just to identify it as the argument of the logarithm. So this is the base of the argument of the logarithm. This is the argument of the logarithm. And this is what the logarithm is equal to. Okay. So now I can just go into my calculator here and change it to base 10 of, of 0.01. And it's -2. So here we have x is equal to -2. And I want to show you something else important about logarithms, all right? So here we had base 10. Now, if I go in, I'm going to copy, no, I'm not going to copy it. I'm going to bring this up again, functions. Notice this one doesn't have the base written in. It just says log of. So log of 0.01, notice that a log of 0.01 is also equal to -2. That's because if we don't write in a base, it's base 10. So I could actually rewrite, I'm going to move this over a little bit, and I'm going to rewrite it. Log of 0.01 is equal to x, and then the answer is x is -2. So what I'm getting at here is that I can write it with base 10 like that, or I can not include any base, and it's always base 10. All right? Questions so far? Anything I've covered so far here? All right, the next one. We need to convert to a logarithm. Whenever we have a variable in an exponent, we're going to need to convert to a logarithm. So we have log base 2.4 of 33.1776 equals x. And I put the x in front instead of behind, just to show that you can flip it around either way you want. It doesn't matter what the order is there. So on our calculator here, we're going to do log base 2.4 of 33.1776. And that turns out to be exactly 4. So here we have x is equal to 4. So that says 2.4 to the fourth power is exactly 33.1776. Now, on these next ones down here, we have log of 3x is equal to 2. So we can't solve for that because x is not isolated. So here we need to rewrite into exponential form. And it's important to remember that when there is no base written in here, it is automatically base 10. So here we have 10 squared because 10 to the second power. So remember, a logarithm is an exponent. So that means our exponent is 2. So that equals 3x. Well, I know that this is 100. And to solve for x, I'm going to have to divide by 3. So what I will get is 100 over 3, which is 33 and 1/3 is equal to x. Any questions on that one? Okay, I'm going to move on then. Again, there's no exponent or no base written in here, so it's base 10. So we have 10 to the x is equal to, wait a second. This one we don't need to solve. It's already solved for x. If it's solved for x, then what we need to do is just use our calculator. So I can do log of 525. I don't need to write in the base 10. I can just remember that it is base 10 right there. So the answer is approximately, so x is approximately equal to 2.72. On the last one, here, x is in the argument of the logarithm. So we're going to need to convert this to an exponential with base 10. So 10 to the 0 is equal to 2x. Well, 10 to the 0, 10 to the 0 is 1. So this is 1 is equal to 2x. Dividing by 2, x is equal to 1/2. And that's how we can solve logarithms and exponentials using sometimes logarithms, sometimes exponential functions. It just depends. All right. Now, y is equal to a to the x is equivalent to x is equal to log base a of y. So a is called the base of the logarithm. And I would include here, y is called the argument of the logarithm. And you can always just write log instead of logarithm. That is just fine. To calculate your answer, use the change of base formula. So I'm not going to focus on this too much, but this is something that I don't know if, do you guys care about like how when I was young, I had to walk to school up hills both ways in the snow with no shoes? Do you guys find that stuff interesting? Do you want to hear like a story about that kind of deal, mathematically speaking? All right, thanks, Tommy. So you guys have these awesome calculators and Desmos and all this technology that allows you to calculate things that we couldn't calculate when I was a kid. Um, there was no calculator that I had access to, and I don't know if one existed that calculated logarithms. So what we had to do is there would be a handout, both sides filled up with logarithm estimates. And all of the estimates were log base 10. Now, look at all these problems. There are loads of problems where the base is not 10. There are all these other bases, and we had no way to look at this page of estimates and figure them out. So what we would have to do is we would have to convert logarithms from some other base to log base 10. So for instance, if we had log base 3 of 14, we would have to rewrite that as log of 14 times log of 3. And then there would be an estimate for log of 14. There would be an estimate for log of 3. We would multiply those together and get our estimate for log base 3 of 14. So this change of base formula was absolutely essential before we had the technology that you guys have right now. Now, you don't really need to know this change of base formula for most kinds of problems that you're going to get here. However, there will be some kinds of problems that you won't be able to answer unless you know this change of base formula. And we'll focus on that later in the unit. Does that sound like walking uphill both ways in the snow with no shoes to you guys? Or not so bad? All right. So we're going to return to question 1e and solve the equation using a logarithm. So let's see. Is it from our warm-up? Was that it? No, it's in the handout. So the question here was 1e. How many years would Greta need to keep her investment of $1,000 at 13% to afford a $500,000 property? So I'm going to write the equation on the slide, and then I'll come back to that slide. All right, so here is the equation that we're talking about. So we said that we would first divide by 1,000. We would get 500, is equal to 1.13 to the x. And now we can rewrite this as a log. X is equal to log base 1.13 of 500. And then we'll get an answer for x. So we're going to go to our calculator. So log base 1.13 of 500. 50.849. So again, we see that you could estimate this, and we can find it on a graph, but now we can answer the question using logarithms, which is awesome. It's always nice to be able to answer questions using using our algebraic skills. So that's the end of today's lesson.